Can everybody hear me well? I hope so, at least. Perfect. So I'll start with a quick presentation on an introduction to TSN. So basically, the idea is to give us some background information on how TSN works, because it's basically a set of standardization. And here I just want to give you a brief overview on the basic mechanisms that we also rely on later on in our tutorials. Okay, a brief presentation outline. So we start with an example use case, give us some basic terminology, and then basically what does TSN? TSN provides us some traffic shapers to shape basically traffic at each hop, at each bridge in our network. And there's, of course, different types that can be used here. So depending on the different requirements that we need, here TSN provides us different techniques. So here I want to present the main three, which are the time-aware shaper, the credit-based shaper, and the asynchronous traffic shaper. And then finally, for wireless TSN in particular, we do require additional mechanisms to enhance reliability. And they're the basic two mechanisms that we need are per-stream filtering and policing, and frame replication and elimination. And here I also want to give you a brief overview. Okay, let's start with an example use case. Here we have a printing machine where we have different motors that require synchronization. So you can imagine an industrial printing machine where you have a printing that goes around 500 meters per minute. And what was usually done before was the employment of the Königswelle. So to synchronize all the different printing units, you could then have different axes and one main drive to power up the whole system. And instead of doing that, what we are currently doing, or a modern system would do, is to have different motors powering the individual printing units. Mikro ist doof. Yeah. Okay. So the different printing units are then powered by an I'm sorry. That's no, it's not. I'm simply holding it this way. That's much easier. So when powering the different printing units by individual motors, what do we have to do? Well, we have to synchronize the motors, because as soon as we have a small deviance between those, we immediately have a paper jam. So here we really require synchronized motors to ensure all is coordinated well. And that brings us to some stringent requirements, of course. And for this purpose, I want to show you also some basics, what we require as typical requirements for such systems. We can also have a classification of real-time protocols. So depending on the different layers where we're at, we can provide different techniques. So on the transport layer, for example, we do not have much control over the individual hops in our network. We only have basically the endpoints that we can control. So there we can only have a coarse-grained control over our system. And instead, what we are now looking at is TSN, which is located at the data link layer. And here we do have control over each individual TSN bridge in our system. And here we can basically have full control over our network. And as a small recap more, here's an overview of Ethernet frames. So basically, I think everybody knows that we, of course, have a destination MAC address, source MAC address. We have the client data and a type and length field. And what TSN now extends this header by incorporating also a Q tag in such Ethernet frames. So here we do then have the opportunity of including a priority code point, which basically provides us some priorities of different frames, which we later use to prioritize different types of traffic. And we also have the VLAN identifier, which is basically a local broadcast domain, which we can use. So how does a network typically look like? Here in TSN, we have different end stations and bridge. So here in blue, you can see the TSN bridges, and in the white boxes, they're the end systems. And now a network TSN flow is here depicted in red. So you have one talker, which is the origin of the TSN flow. And you have basically a multicast tree to different listeners. So listeners can subscribe to a coordination message, for example, to receive the information from a talker. And importantly here is not necessarily that the messages are received fast, but in real time. And real time and fast are not necessarily the same thing. So here it depends basically on the requirements that the stream gives. And that may be, for example, the end-to-end latency. So if we have a talker here at the upmost row and a listener down here, we can basically define that we have some sort of receiving interval. And the packets have to arrive within that interval. So here, packets arrive between dmin and dmax, and we basically define constraints on that interval. That means dmax has to be lower than some sort of end-to-end latency that we have to satisfy, and as well the receiving interval can also be constrained. So the length, the width of the interval can be defined or constrained by some jitter interval. For this presentation, I'd like to focus on time-triggered traffic and rate-constrained traffic. So time-triggered traffic is typically characterized by being periodic. So you send a packet every few milliseconds, for instance, and you also have a defined frame size. And typical requirements here are that frames have to arrive within a certain deadline or latency, and you also typically have a low tolerance to jitter and frame loss. In contrast, you can also consider rate-constrained traffic, which are typically audio or video traffic. And there you have a different type of characterization, which is more like a token bucket. So you may have bursts of packets, which are not necessarily adhering to periodic traffic, but you may have something like this, where you have a short period of time where you don't have traffic, but then you have a larger burst, and you need some sort of pattern to cover that, and that's typically a token bucket. Does everybody know what a token bucket is? Okay. So basically, you can imagine having a bucket which fills with a constant rate of water. And if a packet arrives, you look if you have enough tokens accumulated in the bucket. And if that's the case, you may send out the packet, meaning that if the bucket is full, for instance, and multiple packets arrive, you are allowed to send them all out as long as you have enough tokens. But as soon as the bucket is depleted and doesn't have enough tokens left, you have to either discard the packet that is incoming, or you have to wait until you have enough tokens. And that's a different type of characterization, of course, instead of having a periodic traffic. But that also means, for instance, if we look at the yellow or the orange curve here, that as soon as we have a certain duration where we do not have traffic, then we can no longer come to the initial possible traffic that we can send. So at this point, we are now only able to come up to the dashed curve and are no longer to jump to the black arrival curve. up here, for instance. And of course, there are different, many more traffic types that we can consider and that are also considered in TSN. So, for instance, we may have different alarms and events which are sporadic traffic. So here, sporadic traffic is typically unknown when it happens. So we do not know at what exact time point an alarm is going off. So instead, you then have to be able to provide these guarantees for arbitrary time points, which is also quite hard to achieve, of course. And also for video and audio, you typically have different sort of requirements that do not only account for latency and jitter, but also bandwidth. And here you can basically have the full spectrum that you need to cover. Okay, so what we saw before is that you basically have one talker where the stream originates, and you can have multiple listeners. And now the first question that may arise is how to coordinate or basically how to set up such a stream. And here there are different also basically two main protocols that can be used. So you can have a coordinated or distributed approach where you have a stream reservation protocol where the talker basically sends out an advertisement that he has in stream available that he wants to send out to listeners. So here the talker sends out an advertisement with its traffic specifications, and bridges basically forward the specification. And at the listeners, as soon as a listener receives this notification, it can then decide if it should answer and wants to subscribe, or simply it can also discard the notification if it's not interested. And here it's also possible to already consider the latency, for example. So by looking at the propagation delay or by the accumulated traffic packet delay in our network, the listener can already see if it would violate that requirement that it may have. So if that's the case, instead of sending a listener ready, which we can see up here, we may already send simply a listener failed. And there you then have different sort of optimizations that you can do. So the bridges can accumulate the different answers and can then send a response that is accumulated to the talker, which is then basically set up or sent up the protocol stack for the application to decide what to do. So here, there are basically two things that are interesting at this point. So first of all, that was standardized in 2010. But of course, the standardization advanced over the years. So for new standards, which came up in 2016, for example, with the time-aware shaper, or 2020 with the asynchronous traffic shaper, I think, here we may already see that this simple protocol no longer suffices, and we may need some alternatives. And also the other thing we can see here immediately is that we have a distributed protocol. So we do not have a global view of our network, which may complicate things when we want to compute a schedule. So basically the idea here, or the question I'm imposing here would be at which information can I use as a scheduler? And also where should the scheduler reside to compute a schedule? So, and I think the people who standardized or work in standardization asked the same question and came up basically with a global network entity or a centralized network controller, the CNC, which basically accumulates a global network view of the time-sensitive network and can use this view to support more modern TSN features like the time paper to have a point, so the centralized network configuration controller, which then is able to compute a schedule using this global view. So while we said before that you may ask questions at any time, I'm now taking the time to ask you if you have any questions so far or if it's going too fast. So also to the online audience, if you have any questions at some point, feel free to interrupt me, please. So far, so good. Perfect. Then let's jump into the more advanced traffic shapers. And for that, for us to understand traffic shapers, we first have to start with a TSN bridge model. So how does a TSN bridge look like? And here we have a port-to-port model of a TSN bridge. So we have ingress ports at the top where the packets or the frames come in. We may have some sort of active topology enforcement, which checks are the frames even allowed to come in, depending, for example, on the source MAC address, on the VLAN tag, and so on. And if that's not the case, we simply discard them. Also, we may have more advanced ingress and egress filtering of the frames. So we may specify certain arriving intervals where frames are allowed to arrive, or if they even adhere to a specified token bucket. So if that's not the case, we can also discard them and protect our high priority traffic in the network. So you may imagine, for example, some misbehaving unit in our network which simply replicates messages or hangs in an infinite loop and sends out packets. And here we have to protect, or here we want to protect, of course, our high priority traffic that should not be influenced by such misbehaving units. And finally, at the bottom, we then have our egress ports. And for each egress ports, we have the opportunity to shape traffic. So instead of having a simple FIFO queue, which sends out packets as they come, we can have different opportunities to select or prioritize different patterns of traffic. And what I want to do in the following is have a look, a detailed look on those boxes at the bottom here in gray to see those different opportunities that TSN offers. And we can already start with the most simple form of that. So the strict priority version of traffic shaping would simply say that we look at the PCP values, so the priority code points that we have in our Ethernet frames. So remember, we have a short field of 3 bits in our Ethernet packets that can state the priority of the packet. So here that allows us to basically have up to 8 queues, and the PCP value then decides or basically shows us where the packet should be enqueued. And then the simplest way of shaping the traffic would be to say, well, I'm looking at the PCP values, and the higher the PCP value, the higher the priority. So in this case, we have a traffic class 7 of the highest priority, and here packets will be sent out first. So as soon as a packet is in traffic class 7, we send out that packet, and all the other packets have to wait. So the only delay that a frame of type 7 here can experience would be if already another frame is transmitted. Of course, we can't, by default, we cannot preempt a frame transmission. So in this case, the policy here would be simply to say that the first frame of a queue is eligible for transmission if all upper queues, all queues of higher priority are empty at this point in time. And here the example would then be that we simply transmit all 3 frames of type 7, then the 1 frame in traffic class 6, and then finally at the bottom, all the best effort frames that are left. And here the question to the audience would be simply, can you think of any potential problems that may occur here? Or is all good and we can just go home? Exactly. So what was just said, and that's exactly the point, is as soon as we have some sort of traffic in higher priority classes that are simply starving basically the lower priority classes, we cannot provide any more guarantees to the lower priority ones. And that's, of course, undesirable. So what we instead have to do would here be also to shape the higher priority classes to ensure at least some guarantees, basically for traffic class 6 or the lower ones as well. So let's continue with a few more advanced shapers that are basically also designed to fix this flaw. Starting with the time-aware shaper, so the 8.2.1 QBB extension of TSN defines the time-aware shaper, which came around in 2016. And here, it's quite a simple idea from how it works. So we basically have two different things that we have to consider. First, the online mechanism, basically how the bridge behaves at runtime, and also how to configure the bridges. So these are two different problems. And right now, I just want to have a look at the online behavior of the bridges. So here, basically, the idea is to have a gate located at each egress queue at each port. So remember, we are only looking at one egress port right here. The same is done basically for every egress port and every TSN bridge. And the idea here is to have a queue located at each queue that says if the gate is open, frames may pass, maybe are eligible for transmission, and otherwise the gate is open and frames have to stay in their queue. Meaning that, for example, if we want to prioritize or want to allow a certain guarantee for traffic class 6, we can simply close the gate at traffic class 7 to avoid starvation. And the simplest way of configuring the time-aware shaper is by using a gate control list. So the gate control list basically says for each time point how should the gates, what the states of the gates are. So basically, if the state is open, or if the gate is open or closed at this point in time. So we basically have a list that says for each time point and each queue, whether it's O for open or C for closed. And that's basically all the TSN bridge has to know. Of course, it's an entirely different problem of how to compute such a gate control list. And that's basically, here we can show that it's as hard as chop shop scheduling, which is an NP hard optimization problem. So there's basically our research going in on how to compute efficient gate control lists that can provide formal reliability guarantees. Okay, so also here we can then summarize the policy saying that the first frame of a QI is eligible for transmission if the gate is open and no other frame of a higher priority queue is eligible for transmission. All right, and here we basically again have a simple question for the audience as to how which frames are eligible at this moment. Okay, exactly. So and after that, exactly. So here we would have 6, the first frame, and if the states of the gates are the same afterwards, we would then start transmitting the frames of Q0. Whereas in traffic class 7, of course, the gate would be closed at this point, and the frames would have to stay in their queues. So another thing that we have to consider here is what we previously said, is that the transmission cannot be preempted arbitrarily. So what we also have to encounter for is to have some sort of guard band that ensures that if a gate is open for a certain interval, that no other frame is transmitted at that point in time. And that's exactly what a guard band does. So here, for instance, we have a simple topology on the left-hand side with talkers T1 and T2 that send out frames F1 and F2. And here we want to ensure, using those guard bands, that within their allocated intervals, the frames F1 and F2 can be transmitted. If we do not have guard bands, it may occur that, for example, best effort traffic is sending a maximum Ethernet frame of 1,500 bytes, and that can then overlap with our required interval right here, and that's something we do not want. So what we basically do with our guard band is to ensure that we close off the gates of all other traffic classes to ensure that no frame is allowed to start its transmission within that previous slot, which would then be the guard band. And that's basically all that we need to know for the time-aware shaper. So now at this point, you already know how the first traffic shaper works. Okay, so at this point, however, we only looked at time trigger traffic. What we can also do is have a quick look at rate constraint traffic, because right now, of course, by simply opening gates and closing them, we would have to work quite fast to ensure the same for rate constraint traffic, and we would also require to know the level of burstiness of audio traffic, for example. So gate control lists do not allow us to specify opening intervals for audio traffic without knowing when the burst would arrive. And of course, at design time, at the time where we compute the gate control lists, we do not know that. So here we do need other mechanisms of providing guarantees to audio and video traffic, for example. And the first mechanism would be the credit-based shaper, which is here now placed instead of the gates. So before we had here some gates which can be opened and closed, but instead of that, we now employ the credit-based shaper, which is also a mechanism per queue. So that's also quite crucial. So we do only have mechanisms per queue and not per stream. So remember, by only having 8 queues, what happens if we have more streams than that? So if we have, for example, 16 streams, there needs to be some queue that shares, or some 2 streams that share the same queue. And here we only can provide guarantees per queue. So how does the credit-based shaper work? Basically, we store how much credit the queue has for each point in time. So if we have enough credit, or basically positive or 0 credit, we are allowed to transmit a frame. That means, for example, here, the idle slope, where we have positive credit, here a frame is enqueued and needs to wait because a higher priority frame is currently transmitting. And during that time, we can then accumulate our credit and then send out later at time T2, we can send out multiple packets. So at this point, we would have that at T1, a frame arrives, has to wait until T2 to transmit because higher priority traffic is sending beforehand. And at time T3, however, another packet could be sent because we still have enough credits left. However, as soon as we get negative credit, we would have to wait to accumulate enough credit again until T5 to send out a third packet. So here again, a quick question to the audience would be, what state do we have to store for each CBS managed queue? So before I said we basically have to store for each point in time how much credit we have, but that's not necessary. That's not necessary. So we of course want to have as little state per bridge as we can have to enhance or to improve scalability. So the question now would be to you, what sort of variable, what sort of state do I need to store for the TSN bridge? Sorry? Okay, so at this point, maybe as a quick counterexample, so the potential answer was the time to transmission. So here at T1, a frame would arrive, and he would set a state to T2, saying that at T2 the frame can be sent. But there you do not store an information about how much credit you have at this point. Yeah. Yeah, so but then you would have would have to store two timestamps, wouldn't you? So you would have to store T1 and T2 to basically compute how much credit you have left or how much credit you have at time T2. And that's basically also the idea, but we can also shrink that down to one variable. So we can say we store the time point where we have zero credit, which would be T1. And then we would look at the current time and could then extrapolate how much credit we have right now. And as soon as we hit time T2, we would then see, okay, at this point we have enough credit and can send out a frame. Okay. So the main problem that we have with CBS is that it doesn't necessarily cover a token bucket. So the credit, what we have here on the left-hand side, first needs to be mapped to a token bucket specification that we have on the right-hand side. And here that complicates our analysis somehow. So when we want to consider what guarantees can we provide to our traffic, we need some sort of analysis. And here, typically, network calculus comes in, but that is much easier with a standardized textbook model of our traffic, which would be a token bucket, and not what we have here on the left-hand side, which would be a specific representation of QAV of the credit-based shaper. So for reference, I also included the conversion of how to convert the credit-based shaper credits into a token bucket. And here we basically have two configuration parameters, which would be the idle slope. So as soon as we have credit or as soon as a frame is enqueued, we then generate credits at a certain rate, which would be the idle slope. And when we are then allowed to send our frames, credit decreases according to a send slope. And here we can basically fix the send slope already to be the idle slope minus the transmission rate of that egress port. What we also need is some sort of upper and higher bound. So of course the low credit, the lower bound, would simply be the worst case, which in this case would be hitting zero credit and sending out a maximum sized packet. So here we would have then the send slope times the max frame size divided by the transmission rate. So that's quite straightforward so far. What gets a little more complicated is computing the upper bound. So the upper bound then not only depends on the traffic queue itself, but also on the higher priority queues. So basically here we would require some form of analysis. What is the worst time delay that a packet can experience because all the upper classes are now sending. And that's quite difficult to achieve. So here we would basically require the analysis of the max interference time that we can experience by upper traffic. And that's also the main downside of the credit-based shaper because this analysis can be quite difficult to achieve. But so for the sake of this presentation, let's assume we can do that. For example, if we are located in the highest priority queue, the max interference time is quite easy. And maybe some of you has an idea on what that would be. Okay, the max interference time would only be affected of higher priority traffic. Exactly. So you would have at no. Yeah. So before we said there is one possibility that a frame of traffic class 7 can be delayed. It does that as well, but for the strict transmission traffic shaper, we also had a case there where frames of traffic class 7 can be delayed. And that would be because traffic cannot be preempted. So, for example, if still a best effort frame would be transmitted at that time, we are then allowed to accumulate traffic to send out a burst thereafter. So that for traffic class 7, the max interference time would then only be this short period, basically the maximum transmission delay of a maximum sized Ethernet frame. So at this point, then we can compute a token bucket by simply saying, okay, R would be the idle slope, and so R would be the rate at which the token bucket fills. That's simply the idle slope. And the bucket size, B, would then be the transport rate multiplied by the size of the interval. So the size between the upper bound, the high credits, minus the lower bound, the low credits. And then we can employ basic mechanisms like computing the bandwidth fraction, which is simply then how much proportion of the bandwidth can be allocated to the queue of the CBS managed queue. Okay, so for CBS, we basically have two downsides, as we mentioned before already, and that's also recognized by the IEEE, and they're presented already in 2010 in some presentation. So the basic two downsides would be, first of all, it's quite hard to compute the max interference time for lower priority traffic classes, and the other downside would be that we only can provide per queue guarantees. So if multiple traffic streams are sharing traffic class 7, for instance, we can only provide a token bucket guarantee for traffic class 7, but cannot differentiate for different streams in that priority class. So here we basically have again a trade-off. So we want a scalable solution, which means we do not want to we basically want to store as little state as possible for each TSN bridge. And on the other hand, we of course want to provide fine-grained guarantees. And that's basically also what the asynchronous traffic shaper wants to guarantee. So the asynchronous traffic shaper, the main difference would be that we now want to focus on per frame or per stream guarantees instead of per queue guarantees. And the main thing that we need for that would be to get away from FIFO queues and allow a more powerful form of queuing mechanism. So here the idea would be in traffic class 7 to not have a simple FIFO queue, but basically to timestamp each frame and say what is the eligibility time when the frame is allowed to transmit. So here basically we would timestamp each frame, and that would allow us to send out frame 4 before frame 1. So frame 4 would have a eligibility time of time 0, which would be the first, then frame 3, frame 2, and then frame 1. So the ATS already has to store a little more information per stream. And that also requires that now we do not store credit for the entire queue, but for each stream. And here we can now basically do a similar thing as before by storing the tokens that we have available for each token bucket. So again, we would have some sort of bucket size, which would be here the committed burst size in CB. We also have a committed information rate, which would then be sort of the idle slope of what we had before. But now we also have the possibility of dropping frames. So at this point, for instance, right here, when a frame arrives and would be enqueued for too long, for longer as the maximum residence duration, then the ATS can also decide to drop the frame entirely. And I think only here a short overview suffices, so I do not want to go into any detail for the ATS. What could be more interesting would be the architecture that we require for the ATS to work. So here we have an egress filtering, as if you may remember our bridge model from before. And we first need some sort of classification. So when a frame arrives, we first need to know what type of stream it is a part of. So we have some sort of stream filters here at the top, which first does have to do exactly that. It first has to look at the Ethernet packet, for instance, at the source MAC address, at the destination MAC address, at the VLAN tag, and so on. And based on that, it then has to decide what stream the frame is a part of. And given that identification, we can then map the frame to a certain group parameter, which we see here at the bottom. And that means that we can map two different streams to the same parameters, meaning that they would share their ATS scheduler, but we can also have separate ATS groups for different streams to ensure really fine-grained guarantees at this point. Okay, how much time do I have left? Okay. Then at this point, maybe finally, what I would also like to point out are the common failure models, because that's what we often see gets a little mixed up in literature. So before designing our network, we first have to decide what types of failure models we can accommodate. Here are, for instance, different types. The simplest would be a simple crash fault. So a network entity, which would be a TSN bridge or a talker, listener, end station, basically, can crash unannounced. Meaning, for instance, if we have a TSN bridge at the very center of our network, which crashes, we do need some alternative route to send our high priority traffic over. And the farther we go down here, the more difficult it can get. So for omission failures, we may simply discard individual frames or they get lost, which is of high criticality also in wireless networks as well. And down here, the worst case would be a Byzantine fault, which I would also like to know if any one of you is familiar with that term. That's okay. That's unfortunate. So basically, the Byzantine fault was proposed by Leslie Lamport, which is kind of a god of distributed systems, I would say. And Byzantine faults basically cover the whole spectrum. So we have arbitrary faults at this point, which would mean a bridge would be allowed to manipulate individual headers of our Ethernet frame, for instance, would be allowed to delay it, would be allowed to simply discard it. So here we have no restrictions at all. And it's I think quite intuitive to say that covering Byzantine faults is near impossible if we want to achieve real time at the same instance. So what we really have to consider here would be what type of failures can we accommodate. And one of the main things that I would say is still possible in TSN would be a babbling idiot failure, which is a quite funny term, but basically it says that a network entity can generate unexpected traffic. So for instance, if we would have one malicious talker which would simply spam out high priority frames, meaning frames that have a PCP value of 7, then he could mess up our whole network and our whole guarantees for high priority traffic. So we also need some sort of mechanism to protect specific streams from such faults, and that's what's still possible, I would say, in TSN. But going further than that, so having a TSN bridge in our network which starts to tamper with our Ethernet frames, there, of course, it's getting quite hard to achieve any guarantees at all. So I would say we'll leave it at that. Maybe I can jump to the final lessons learned lecture for this part. What we considered here are the fundamentals in TSN. So in particular, I want to highlight the difference between time-triggered traffic, where we have periodic frames being sent, versus rate-constrained traffic, where we may have bursty audio or video traffic. And here again, the short recap was that real-time guarantees are not necessarily the same as being fast. So here we do want certain latency, deadline guarantees, but that doesn't necessarily mean that we have to be the fastest one arriving. And for the traffic shapers, we then considered the time-aware shaper, which is designed to accommodate time-triggered traffic, and also the credit-based shaper and the ATS, the asynchronous traffic shaper. And the main difference here between those would be that the asynchronous traffic shaper is designed to provide per stream guarantees, whereas CBS is better in terms of scalability, I would say, but only can provide per queue guarantees. And that would be it for the first lecture. Again, if you have any questions, feel free to ask them.